Hey everybody, here to talk again a little bit about some of the descriptive statistics that we try to calculate to, again, define the characteristics of our data set and eventually learn how to conduct those inferential statistics that let us draw conclusions about our populations. So today we're going to be talking about some basics about the ideas behind variability, and we're going to end with a formula for calculating one of the most common forms of variability or measures of variability, which is the variance. So, starting at the beginning, we've already learned about central tendency. And again, central tendency kind of defines one dimension of our distributions. It tries to again pinpoint the center of that distribution, the middle of it. But as we mentioned in that lecture, different distributions can have the same exact average, but can differ quite a bit on what we call variability, how much scores differ from that mean or from that average. So, central tendency does not tell us really anything about the spread or the variability of a distribution. Some distributions are all over the place. Scores are really, really separated from each other. There are big differences between scores. Some of them are very close together, where people tend to score very much the same and the variability is pretty small. So sometimes scores are all over the place. Sometimes they're very, very similar. Again, that dimension is something that we need to know about. That's what these descriptive statistics that measure variability are designed to do. So let's take a very simple example. Let's say that we have two different groups, 10 people in each group, and what we're measuring, our variable of interest, is how many close friends they say they have. So in group 1, all 10 people in that sample just happen to give exactly the same number. They say they have 3 close friends. So there's no variability here. Everybody has exactly the same score. In group 2, you have half of your people say they have 1 close friend, and half of the people say they have 5. So we have, again, different variability there. Here people are differing from each other. Those scores are a little spread out. Here's the thing, if you calculated the mean, in both cases you would get a mean of 3. The average score is 3. Notice that the mean doesn't let us tell these two groups apart. We can't tell that meaningful difference that there's variation in this group but not in this group. The mean will not give us that information. It won't separate between them. So how are we going to assess this? How can we measure that dimension that central tendency doesn't capture, that spread or that variability? There's a very simple way of doing this, which you've probably learned before, called the range. You just take the highest score in the data set, subtract the lowest score from that. It's the difference between the biggest and the smallest score in your data set. The problem here is what we'd call outliers. Somebody who's just really, really far away from every other score is going to make the range look a lot bigger than it actually needs to be. This is one reason why the range isn't often used. So let's revisit our problem here, our two different groups. Again, they have the same mean, but they have differently shaped distributions. How can we assess this outside of the range? Well, we can use that technique that we talked about back in central tendency, deviations. Again, the way that we calculate deviations is by calculating how far each individual score is from the average score. X minus M. Individual score minus average score. Here's the problem with deviations, if you remember it. Because there's an equal number of points above and below average, those deviations work just fine for individuals, but for an entire distribution, they're going to cancel each other out. There are always as many points above the mean as there are below it, so if you add up, notice our sigma here, all of the deviations, it's always going to be 0. Can't tell different distributions apart. So that's a problem. We can use deviations for individuals, but it's useless for data sets. How do we solve this problem? Well, the variance is a descriptive statistic. It's quantitative, and it tries to assess the spread of those scores in a way that sidesteps the problem that deviation scores have. So the variance is based on deviations, but we're going to do some little mathematical trickery to get past that problem where the deviations all cancel each other out. But for now, again, the idea of variance is just that the more spread out scores are, the bigger the number gets. If you have similar scores, if everyone has exactly the same score in the entire data set, here everybody has a score of 2. There's no variance at all. The scores do not differ, they do not spread out. If you have some small differences, like seen here, where you have 3 people with scores of 2, 2 with scores of 3, that's going to have a small variance. The scores do differ from each other, but not by much, so your variance is going to become smaller as well. As differences get larger and larger, like here where there's a much bigger spread between those scores, your variance gets bigger and bigger. So essentially the variance is a descriptive statistic. It's a number. The bigger the number gets, the more spread out the scores are from the average. So here's how we calculate the formula. We're going to work with some sample problems in the next portion of this module. For now, we're just going to focus on the logic of this formula. So here's how variance is calculated in a sample. It's what's called the definitional formula. We won't worry about that just yet either. The first thing you do is subtract the mean from each score. We've heard of that before. That's calculating a deviation. So we start by just calculating deviations. If we added all those deviations up, we'd always have 0, so we're not going to do that. Instead, we're going to square each of those deviations. We're going to multiply each one by itself, right? So what happens when you square a positive number? Well, if it's bigger than 1, it becomes a bigger positive number. What happens when you square a negative number? A negative number when squared becomes a positive number. That sidesteps that problem where all of the deviation scores added up are always going to equal 0. Because now that we've squared them, all of our negative deviations are now positive. So we're going to be able to add them up and get a positive number. So we then do exactly that. We add up all those squared deviation scores. At this point in the process, we don't have a variance yet, but we've calculated something called the sum of squares. Sum of squares is a pretty important concept in the course, but it's a little tricky because we work with sum of squares here and we calculate variance. Then it kind of goes away for a while, and then late in the course, it's going to come roaring back. We're going to be calculating sums of squares left and right. So keep that in the back of your mind. But again, for now, it's just the numerator to our variance formula. So this is what the sum of squares formula looks like. Notice that the steps are captured here inside the parentheses, and parentheses are always calculated first. We see, again, step 1, that's a deviation score. Then exponents come next. We again do everything in the parentheses. Then we do the exponent. Please excuse my dear Aunt Sally. Parentheses, then exponent. So we square each of those deviations. That's step 2. Then comes the addition. We add them all up. That's what this sigma is telling us to do. Add up all those squared deviations. That's step 3. Step 4 is you just divide it by the number of squared deviations you have, which means the number of scores you have. It's sort of like getting an average of that sum of squares. So here's what our formula looks like. A couple of things. S squared is the symbol for variance of a sample. Here we see this little subscript of x. Don't worry too much about that at this point, but what that means is it's saying, what are we calculating the variance of? In this case, we're using that generic term we call the variable x. Later on, when we start dealing with multiple data sets at the same time, that little subscript is going to become more important. But for now, it's just kind of a placeholder that again tells us that we're calling the variable x. So here's that exact same formula here. Deviation scores in the parentheses, squared. We square each one, we add them all up. That's our sum of squares. We divide by the number of scores. Here's that same formula, but this has been shortened to just the sum of squares. So next up, we are going to practice calculating variance, both with that formula and a second version that is designed to be a little bit quicker and more efficient. See you there.